on our end.
Hey, thank you. So we've heard a lot about how these rogue planets form and different mechanisms and so on. I'm going to do a bit of the opposite. I'm going to say that these rogue planets are also going to do something to the solar system or to other planetary systems. So the opposite. This is work that's been mainly done by Garrett Brown, who's a PhD student of mine. He just graduated a week ago. Also collaborated with Rein and Judge Fair Service on this. So let me give you the takeaway first. So what we do in this study is we try to form the solar system with the help of rogue planets. And the scenario is very simple. We start with initially circular and coplanar orbits. We have a flyby, and then afterwards we have orbits of the planets that look very similar to the orbits that we observe today in the solar system. And we think this might be an important formation mechanism that should be considered when we talk about the formation of the solar system. And I'll talk to you about the ingredients and how we get to that conclusion. We've already heard a lot about the initial mass functions, and this talk is no different. We need some initial mass function to say how many small bodies are there in sort of a cluster environment to say whether this scenario is reasonable or not. I'm going to use the Mashberger IMF here. There are differences at small masses if you choose different initial mass functions. But for this study, these small differences actually don't matter too much. It's an order of magnitude estimate, so hopefully these are right. I don't think I need to explain this too much to you in great detail, but I want to bring home the point that there are a lot of small mass objects floating around in the universe. So one way to show this is to plot the initial mass function as a cumulative mass function of the mass. And what you see is that about 50% of the objects have a mass that's less than a solar mass. Or half of the mass is in subsolar mass objects. If we plot the cumulative number as a function of the mass, then it becomes even more important, more obvious that we need to study these small objects when we consider flybys to planetary systems. About half of the objects have a mass of less than 0.1 solar masses by number. And even further, if you go down to about 20 Jupiter masses, then about 20% of the objects are that small. And again, there are some differences between different initial mass functions that you assume, but the take-home story is that there are a lot of small objects. So putting this work a bit in context, people have studied the effects of stellar flybys on planetary systems for a long time. Here's a short list of papers. There are many more that have studied this in the past. Historically, people have focused on the effects of stellar flybys with stellar masses. So these masses, people assume typically a solar mass. Some of them went a bit further. Sean Raymond has a paper with about 50 Jupiter masses. There's some work by Leodal that goes to very small mass, but historically, we were interested in big objects because bigger objects have bigger effects, naively, right? If you think about it, on planetary orbits. And the conclusion for these studies, more or less, is that these objects these flybys are rare, and they might have not really happened very often in the early history of the solar system because if they come too close, they destroy the planetary system. And if they come not quite close enough to destroy it, but become close enough to perturb it, then they mostly perturb the outer orbits. Neptune's orbit, the Kuiper belt, and so on, those get the strongest perturbation. So what we do in this study, we extend the flyby mass range to much lower masses, namely a Jupiter mass. And we'll find a very different behavior. The reason why a Jupiter mass is kind of the important mass to consider is that we want to perturb the orbits of the solar system, and Jupiter is the most massive planet. So we need roughly a Jupiter mass to perturb the orbit, but not much lower. So we don't need Oumuamua masses to perturb the solar system. It's not massive enough. So maybe a little bit lower might be better, but we choose a Jupiter mass as a cutoff. All right, so in addition to this IMF that we're using and this cutoff radius, cutoff mass of 10⁻³ at lower end, we need to assume some other parameters for the local environment in which we think the sun formed. We use a velocity dispersion of 1 kilometer per second and a relatively high mass density of 100 solar masses per cubic parsec. And then we have to assume a lifetime of the birth cluster, a few tens of millions of years. If any of those parameters don't sound right to you, I'd love to hear from you. I missed the first talk of the first day of the conference, unfortunately. So if you gave a talk on the initial mass functions or any of those things, and you have an opinion, please let me know. I'd love to talk to you more. These are the assumptions that we make, and we go from here. All right, so let me talk to you about the setup. We do direct and body simulations to do this work. Analytical work does not work very well here because these are flybys across the orbits of planets. So any sort of perturbation analysis is not good enough to really talk about the details. The initial conditions that we use for the planets are a bit artificial, and we can talk about this later in a bit more detail. What we assume is that the solar system formed all the planets where they are today through some mechanism that we're not discussing, but they're initially circular and coplanar. The circular and coplanar is maybe not super controversial because planets form in disks, the eccentricity inclination might be low, but right precisely at the semi-major axis that we observe them. There's no good justification for that. But we need to start with something, so this is the first step. Then we simulate 50,000 flybys. We randomly sample the mass, the velocity, orientation, and impact parameters from the stellar cluster environment using the airball package. And then we just see what happens to these objects. The impact parameters range from 0 to 75 AU. So these are really close flybys. Again, they cross the orbits of the planets that are already formed in the solar system, which is very different from traditional flyby simulation that people consider big objects that pass relatively far away. So our goal in the end here is to reproduce the solar system. And what we need to do that is we need to determine what is actually a good outcome. When does the planetary system look like the solar system? When does it not? And that's surprisingly hard. One thing we could do is we could just compare the overall parameters of two different planetary systems. Do they have the same major, semi-major axis, the same eccentricity, and the same inclinations? And if they're similar, then it's a good match. The problem with that is that these instantaneous overall parameters don't really describe the nature of the secular dynamical system of a planetary system, where these objects are not on fixed orbits, but their orbits evolve. And this would be lost if we just do that. There are other quantities that are often used to determine the nature of planetary systems, for example, the angular momentum deficit. That is also not a good thing to use here because it might be dominated by one planet, and especially if we have flybys, then it's mostly the outer planet gets excited. So that might just dominate the angular momentum deficit budget and lead to a skewed effect. It's also not good enough to just calculate secular frequencies and amplitudes and compare those to each other, because once again, we're sort of missing planet-planet interactions, this time in the nonlinear regime, because these evolve over the time. So what we do instead is we come up with a new measure, which we call the log spectral distance, that can compare two planetary systems with each other and determine whether they're similar in their dynamical secular architecture. Sam, I can't read any timer. Okay, thank you. Okay. So let me tell you what this new log spectral distance is. So what we do is we run relatively short-term integrations of 20 million years of a planetary system where we record the eccentricities and the inclinations. They're the complex versions of those. Then we plug into this log this spectral distance metric here. So we take the absolute value of the Fourier transformed coefficients, logarithms, take the log, and calculate the difference between two planetary systems this way. What we get out is a single real number, and we can use this number to define what we mean by similar or not similar. It's just a single number that we get out. The nice thing about using this is that it actually satisfies a mathematical definition of a metric, so the triangle inequality, and if you plug in two equal systems, then you will get 0 out at the end as a distance. So now we have a way to measure the similarity between two different systems. But let me go a bit more into detail about how we actually do that. The solar system is not a static system, as I mentioned before. Like the planetary orbits evolve, the secular frequencies evolve. So we can't just compare some random flyby to the present-day solar system and see whether those two instances of planetary systems are the same. That would leave us a very skewed definition of similarity. So what we do instead is we use the present-day initial conditions, perturb them a little bit, and run 96 different evolutionary tracks of the solar system. We integrate them for 5 billion years, which is approximately the lifetime of the solar system, until the sun reaches the end of the sequence. And in those long-term integrations, we could randomly pull out 2,520 million segments, so we can calculate the eccentricities, inclinations, and calculate this log spectral distance. So comparing 2,500 against 2,500 other ones, we can now compare basically the solar system to itself. And we can say, how much does the solar system evolve just by itself, so we know roughly what are the error bars that we're trying to fit if we try to find a match to the solar system. Putting all of this together, and let me show you the results. So this is this metric, this log spectral distance, and I'm plotting the distribution here. If we just compare the solar system to itself, we get this red curve on the left. So this is how much the solar system varies within 5 billion years compared to some random other time in those 5 billion years. And so it's not static. And then we look at these 50,000 flybys that we ran, and we compare those to these solar system samples here. And somewhat surprisingly, there's quite a large overlap between those two different distributions. Like most flybys don't look anything like the solar system. Right? They're very different to how much the solar system varies by itself. But there is this overlap, and it's about 1%. 422 out of 50,000 simulations. Now, 1% might seem like a small number, but I'd like to convince you that the opposite is true. That's a surprisingly high number, that there's a success rate of 1% of a random flyby producing something that looks very similar to the solar system. It's as similar as the solar system is to itself. It can't be 100% because then every planetary system in the universe would look like the solar system. So that doesn't make sense. So 1% is a reasonable number. It's not infinitesimally small. It's not a needle in the haystack. We have a lot of samples that we found. And now, so the takeaway point is that the samples that we find that are a good match, these are the blue points in this graph, are all low mass. So they have 10 Jupiter masses down to about 2 Jupiter masses, and they're very close by flybys, a few AU in general. So they cross the orbits of the planets, and they don't destroy the planetary system, but they perturb it enough. Let me show you the best match. So here's the simulation of the initial circular coplanar solar system. Flyby comes by, gives it a little kick, and now we have perturbed planetary orbits. Visually, you don't see a big difference, but this system now dynamically is very similar to the present-day solar system. Just the same simulation from the angle, in a different angle. Now everything is coplanar initially. Flyby comes by, excites the eccentricity, the inclinations a little bit. And again, these inclinations that we see are very similar to the present-day solar system. Just one more different way of looking at these results. I'm showing you the spectrum of the eccentricities and the inclinations of the other planets in the solar system. The black curve is the data that we have for this best match flyby. And in color in the background, the shaded area, this is the spectrum of the solar system. And what I want you to look at is that these peaks, the peaks of these secular frequencies, both the amplitude and the location of these peaks is very similar to the solar system. The solar system is not a solid line, but this spread out line, because again, the solar system varies within 5 billion years. So this is one match that fits roughly within the same range as the solar system moves by itself. Okay, as a summary, the chance of such a flyby happening is very high because we now know that there are these rogue planets out there. With the values that we've assumed, there's about a 10% chance that something like this will happen. If it happens, then we don't necessarily destroy the planetary system, even though this flyby comes really, really close. And instead, we might actually reproduce something that looks like the solar system from something that was initially very different, namely coplanar and no eccentricity, with a high probability of 1%. So clearly, I don't want to claim that this kind of an information scenario explains absolutely everything we see in the solar system, right? That cannot happen, but it might be one important part in shaping these planetary systems. And maybe one one way to look into this a bit more is how this might work with other formation scenarios. If you form the solar system and initially your planets end up on circular orbits, you need to take into account what flybys do to it, because they are not very rare and they will alter the planetary system. So this could, for example, trigger some instability later. We don't think the LHB is an issue anymore, but this could easily explain how LHB-like instability could be triggered, because initially something is stable, the flyby perturbs it a little bit, and then it goes unstable a bit later. Okay, that's it. Thank you.
Thank you for the talk. That was really interesting. So I was wondering, sort of to the last point you were making, can you make any predictions for like other dynamical scars that you would see in the solar system?
Other dynamical
scars of a process like this, right? Because you were only looking at the giant planets here, I think.
So we did some more work. So this is the full solar system, including all the terrestrial planets. And surprisingly, again, such a flyby does not really destroy the inner planets at all, even though it flies close to Mars's orbit. And in fact, it excites the eccentricity inclination of the inner planets as well, two values that are very similar to the observed ones. They're more free parameters, right? So it's more fine-tuned if the more constraints you add. So therefore, I'm not sure how to quantify the probabilities, but it's not inconsistent. And same thing with like small body populations like the asteroid belt. If we initially have a very cold asteroid belt, we have this flyby, we excite the eccentricity inclinations a little bit to, again, values that are not inconsistent with current observations, but it doesn't destroy the asteroid belt, for example.
Cool.
So I was a little confused. So I asked this question on day one. What's the probability of these streak-on planets that are flyby in the planetary system? Sean mentioned there was 1% per billion or 10 billion years. And then you're saying it's 10% now. So I'm curious on how you're getting that.
Sean, do you want to say why your number is different?
Oh, it's the cluster phase. I was talking about the field. So your question the other day was about in the field. So when, in the present day sun orbiting the galaxy. And this setup is for the sun's birth cluster.
Okay.
So it's different velocities and different frequency of account.
And the high density of stars. Right? And again, if someone thinks this is not a good assumption for the birth cluster, let me know. What do you think is better?
Hi. Okay. Very nice. So, I'm interested in the effect of your too much flyby to the transient ocean. So, for example, you discuss the formation of cellular-like detached objects by the stellar. So, with your too much flyby, can you make that kind of object?
I think there's another talk later, right? We talked about this more. Yeah, I'm looking forward to your talk. I don't have much to add here. We did do some sort of quick test on what it does to initially a cold feather belt, and whether we can excite it to some sort of observed values. We didn't look at the options that you mentioned specifically. Could be something for future work, but I don't think it will affect them a lot, right? These are wide orbits. The orbital periods are long compared to the flyby time scale. So it's kind of an adiabatic thing that will not be perturbed much. But there could be other flybys, right? There could be other flybys that. So this might be one flyby that does something to the more inner solar system, and then another flyby, maybe a more massive star, does something to the other objects.
Yeah, I was wondering how often do you capture the flyby?
Doesn't happen.
Doesn't happen never.
No.
Yeah, I have a quick question. So, if you think that there is a flyby with closest approach at 1 AU, in average, due to the randomness of this encounter, this should be roughly 100 flyby at 10 AU. That's just due to the impact parameter, the frequency scaled by impact parameter squared. So if one 1 AU or less than 1 AU flyby can make the solar system, that 110 AU flyby would surely destabilize the solar system, I think. Or just make a solar system that's unlike a single flyby.
Yeah, so you're asking about, I think you're asking about multiple flybys. If you have
Yeah.
one of those,
Yeah.
you're expecting also to have ones that are further out and you have more of them because the cross section is bigger for those.
Yeah.
Yes, it becomes a statistical question. Like, how likely is it to have this one but not enough of the others? I'm showing you one flyby that does something. There could also be 10 smaller, weaker ones that add up and do something similar. I don't think it's it has to be one or the other. But yeah, I think looking at multiple flybys is a good suggestion. Yeah.
Okay. Oh, one more question. Jay.
Really interesting stuff. One of the things I'm wondering about is if you allow for the evolution of star cluster properties. So, for example, the Orion Nebula cluster is one hypothesized type of region of the sun could. And we know that regions like this have a cool collapse phase where they have extremely high densities for a very short amount of time, and they expand, throw out a lot of things, reduce their density while have you considered that?
I mean, for us, what really matters is just the encounter rate. So if there's a dense phase and not so dense phase, all that matters really is the integrated average density. So I don't think it matters much. It might matter a bit if you take into account the velocity of the stars. We have a preference for 2 kilometers per second or something for these flybys to do something that ending up in something that looks like the solar system. So I think the velocity component might be interesting, but otherwise, yeah, it's just an integrated thing over the entire lifetime.
So does flyby set the limit of the most outer planets?
Yes, if there's a flyby that is, especially if it's massive, that comes by, it will shake up the outer solar system primarily. And given that we have planets out there, there is a limit that we can't have had a solar mass object passing by Neptune's orbit, but did not happen. So yeah, we can quantify that more, but yes.
Again.